Welcome back, Focus Learners. So I am absolutely pumped for today's explainer, because we're looking at a breakthrough that, well, honestly, it feels a little bit like magic. We're going to explore how artificial intelligence is quite literally breaking the physical limits of consumer hardware. Now, we always talk about software making things faster, right? But what happens when software allows us to bypass the physical constraints of the very devices we wear every single day?
Just think about this for a second. How exactly do you cram 6 microphones into a tiny little earbud without making it bigger? It sounds like a riddle, doesn't it? See, if you want to capture pristine, professional-grade audio in a noisy room, you typically need a large array of physical microphones spread out over a distance. But in the real world, we want our devices, wireless earbuds, sleek smart glasses, to be as tiny and invisible as possible. So, how do we get that massive array audio quality without the massive hardware? Well, today, we are going to completely unpack this brilliant illusion of hardware mystery.
Okay, let's dive into this. Here is our roadmap. Today, we're going to cover the hardware size problem, meet the research team behind this, unpack the concept of virtual microphones, dig into the spatial magnifier architecture, review some wild test results, and then finally explore what this means for the future of audio. All right, Section 1, the hardware size problem, or as I kind of like to call it, physics versus audio. So here's the fundamental frustration we always hit with consumer electronics. In the world of multi-channel speech enhancement, there's this golden rule. Increasing the spatial diversity of your microphone array, meaning spreading the mics further apart, or simply adding more of them, massively boosts your audio quality. More microphones mean better spatial directivity and far less background noise. But look at the devices we actually use daily. Augmented reality glasses, wireless earbuds, hearing aids. Their spatial capture capabilities are strictly limited by physical reality. I mean, you literally cannot fit a bulky 10-microphone array onto a delicate pair of glasses. We hit a wall where the laws of physics just dictate the limit of our audio quality. Moving right along to Section 2, let's meet the research team.
The source material for our explainer today comes from a genuinely fascinating paper titled Spatial-Magnifier, Spatial Upsampling for Multichannel Speech Enhancement. And this is the result of a powerhouse collaboration between Meta Reality Labs Research and KAIST, that's the Korea Advanced Institute of Science and Technology. We've got an incredibly talented roster of authors here too, including Donghyun Lee, Ashutosh Pandey, Sanjil Parekh, Daniel Wang, Jacob Donley, Buye Zhu, and Juan Hazcarreta. These researchers aren't just making incremental software updates, you guys. They are fundamentally redefining what tiny hardware can actually do.
Which brings us to Section 3, creating virtual microphones. This is basically where the magic weapon gets forged. Now, to really grasp what this paper is doing, we have to understand what a virtual microphone, or a VM, actually is. In the context of neural network-based virtual microphone estimation, which we're just going to call neural VME, a virtual microphone is a captured audio signal that is available to the AI model during its training phase, but it's completely absent during inference, which is when the model is actually running in the real world. Think of it as a ghost microphone. The AI learns what that extra microphone should be hearing, even when it isn't physically there to hear it. So what Neural VME does is it estimates these missing virtual mic signals from a really sparse set of actual, real microphone measurements. It's kind of like, imagine having a blurry, low-res photograph and you use AI to upscale it into a crisp, high-definition image. The spatial magnifier is literally doing exactly that, but for spatial audio. It takes the audio from, say, just 2 physical mics on your smart glasses, and it artificially generates the audio signals for 3, 4, or even 8 additional virtual mics. It effectively increases the array's spatial diversity without adding a single ounce of new hardware. All right, Section 4, the spatial magnifier architecture. Let's look at the engineering behind the magic. So, the spatial magnifier uses this highly specialized AI network that's tailor-made specifically for spatial upsampling. It takes the real microphone signals and runs them through these alternating blocks that are meticulously designed to exploit the subtle relationships between the audio channels. Instead of just trying to clean up the sound it already has, the network pulls out the tiny spatial clues hidden in the real microphones so it can accurately hallucinate the virtual ones. But look, having a crazy, complex AI model doesn't do you any good if it totally drains your earbuds battery in like 5 minutes, right? So to solve this, the researchers built in 2 super efficient modules. First, the selection module. It acts as a filter that finds exactly the right audio clues, dynamically. Then you've got the dynamic channel allocation module, which decides which of those clues are the most important so it can efficiently compress the data. The result? You get a massive boost in performance with very minimal computational overhead, which is what makes this tech actually viable for consumer wearables. Now, once those virtual microphones are generated, they get fed into a framework called SARL, Spatial Audio Representation Learning. And SARL's job is to take all that rich, newly generated spatial info and use it to actually clean up the final audio. And what's super fascinating here is that SARL pulls this off in two different ways. The first is signal level augmentation, or SARL-S. This is where the model essentially hands the system raw, artificially generated audio tracks to work with. It literally gives the system more audio to listen to. The second is feature level augmentation, or SARL-F. Instead of raw audio, the AI feeds the system a high-level conceptual map of the audio space. This helps it separate sounds even when recreating the exact waveform is just too difficult. But both methods effectively trick the enhancement model into thinking it has a much larger physical array. Okay, moving into section 5, testing the virtual array. This is where AI actually starts beating hardware. Guys, the crucial breakthrough here is the 2+1 setup. The researchers found that an array of 2 real microphones plus 1 AI-generated virtual microphone actually suppress noise better than a flawless physical 3-microphone baseline setup. Just think about that for a second. The AI hallucinating a third microphone resulted in better speech enhancement than actually having 3 real microphones. The AI's training process creates highly optimized spatial representations that guide the whole system better than raw hardware does. And they definitely didn't stop there. They pushed this to some extreme scaling. They tested a 2-channel real plus an 8-channel virtual setup, and it performed incredibly close to a massive physical 10-channel system. They even proved this works in the real world by simulating how sound actually interacts with the physical shape of smart glasses. Furthermore, they demonstrated that using this virtual microphone strategy achieved higher speech quality at significantly lower computational costs, compared to the lazy alternative of just making a standard neural network bigger and heavier. It's versatile, it's architecture agnostic, and it's highly efficient. Finally, section 6, the future of audio. Let's talk about erasing those physical limits. Let's bring all this complex architecture back down to earth for a minute and talk about why this actually matters to you and me. The spatial magnifier essentially proves that we don't have to compromise on audio quality anymore just because our devices are getting smaller. This software effectively bypasses the physical limits of hardware design. It enables the kind of massive array audio clarity you would expect from a bulky studio setup, but it tucks it all right inside the tiny physical constraints of the sleek smart glasses or earbuds you're already wearing on your commute. And that leaves us with a pretty profound thought to end on. We've just seen how specialized AI networks can convincingly hallucinate physical sensors that don't even exist, and actually outperform real hardware in the process. So if AI can successfully simulate hardware we don't even have, what physical limits will software erase next? Thanks for joining me for this explainer, focus learners. Keep exploring, keep questioning, and I'll see you next time.